Hey everyone, welcome to another video. In this video, we are going to solve the question of max stack. So this one is a lead code hard problem, and we are going to make use of everything we have learned so far in our previous videos. Before solving this problem, I highly recommend you to solve these two problems of LRU cache and design Twitter, because it's going to be really hard to solve this question without taking the learnings from these two problems. So please solve these two problems first. Seeing this problem for the first time, I thought it's a really straightforward problem. Like, what could be difficult in this problem? Because we just need to implement a stack. So as you know, a stack is a LIFO or philo data structure. So what this means is it's a last in first out or first in last out data structure. So let's say if I have my stack elements in an array or any other data structure, so I add the elements at one end and remove it from the same end. So the element which was last in, it's going to be removed first, and the element which was first in, it's going to be removed at last. So these three functions, top, push, and pop, are basic operations of a stack, and they are really straightforward to implement. What makes this problem complicated are these two functions that we have to implement, which is the peekMax and popMax functions. And also our stack can also have duplicates. So it can have duplicate elements. So it could have something like 1, 1, -1, -2, 4, 4, or -1 could be here, and we have to work around with duplicates. So for example, let's say 4 is at the front of the stack and a call comes to remove the max element. So as we know, the value 4 is the max here, so we want to remove this value and not these two values. So it's like we have to keep track of the timestamps at which a particular value was added to the stack. We have to implement our push, pop, peekMax, and popMax functions in logarithmic time, and our top function should take O of 1 time. So to just get things started and without worrying about time complexity, and just to make the code work first, so let's assume that our stack is in the form of a singly linked list. So if it's a singly linked list, then let's think about all these 5 functions. So if we are going to push to our stack, so we can simply add it to our head and remove it from our head. So if let's say a new node comes in, let's say 5, so it's going to be simply come at the head, and 5.next is going to point to 4, and node 5 will become our new head. And if let's say top call comes, then we can simply return head.value and we'll be done. And now let's say pop call comes. So for pop call, we are going to remove the node at the head, which is the node 5. And so what we can do is we can first store this head reference somewhere in a variable, and then we can update our head equal to head.next, and now node 4 again becomes our new head, and we will be done. For our peekMax and popMax functions, what we are going to do is we are going to start at the head of the linked list and we are going to iterate over it. And as we are iterating, we are going to keep track of the maximum value and store that node somewhere. And for our peekMax, we can simply return node.value. And for our popMax function, so let's say this, instead of value 3, it's value 13 here. And let's say I reach here. For our popMax function, we also need to remove this node. So to remove this node, I'm also going to need a reference to the previous node. So as we are iterating, we are going to keep track of previous node as well. And once we find the maximum, we're going to just update previous.next equal to 13.next, and we'll be done. For the case when there can be more than one node with maximum value, for example, in this linked list, the maximum value is 4 here. And for the popMax call, we need to return this node. So for that, we can do 2 iterations, 2 O of n iterations. So in the first iteration, we can simply find the maximum value, and in the second iteration, like once we reach this node, and we are also going to have the previous reference. So if like current.next.val becomes equal to max, then we can simply update this pointer here and point to this node. And once we do that, we can simply break out of the loop and we will be done. So for singly linked list case, so these 3 calls are going to be O of 1 time, and these 2 calls are going to take linear time, and we need to improve this linear time complexity to logarithmic time complexity. And this O of 1 time complexity for these 2 functions can get worse and can become O of log n, which is okay. And let's say if we were using an array instead of a singly linked list to store our stack values, then also it's going to be linear time complexity. So for array, if it's a fixed size array, then we're going to reorder elements, and if it's an array list, then array list uses a circular buffer, and then again it's going to be linear time complexity. So now let's try to improve our time complexity to logarithmic time. Doing a popMax call for our stack is like removing a random node from our data structure. For our popMax call, we need to remove this node from our data structure. So the data structure which helps with removing a random node in O of one time is a doubly linked list. So with the doubly linked list, we don't need to iterate over our data structure from the head, and we can simply make use of next and previous pointers to set the pointers of previous node and next node, and we will be done. Now we have a doubly linked list here, and now let's say the value at head is 13 instead of 3. So now a call comes to remove the max element from our doubly linked list. So now what's going to happen is 13 is going to be removed, and our new head is going to be at node 4 here. Now what happens if another popMax call comes in? So now it's going to remove this node 4. When we were creating this stack, we are going to make use of push function call, and as we are adding elements to our stack, let's say we use a global variable max to keep track of the maximum value. Now what happens if this maximum value gets removed from this stack? Then we are going to need a second maximum value, but we were not tracking this second maximum when we were adding to our stack using push. Now which data structure is going to help us with tracking the second maximum if the maximum value gets removed from our doubly linked list? Think about it. It's a max heap. So along with a doubly linked list, we are going to make use of a max heap. Now to create this max stack data structure, we are using a combination of doubly linked list and max heap. This doubly linked list is keeping our philo or LIFO structure, and this max heap, it is going to help with tracking the maximum elements, the first maximum, second maximum. So if the first maximum gets removed, the second maximum is going to be the first maximum. And now if let's say the second maximum, which is the current maximum, that gets removed, then it's going to update the maximum in our max heap as it is updated in the stack. Let's try to understand the flow of popMax function when we have a doubly linked list and a max heap. I have updated the head value as 3 now instead of 13, so that our max value is 4 now. So as you can see, we have two nodes with values 4. popMax function should return the node which is closer to the top of the stack. So when we were adding all these nodes to our stack, we were also adding it to our max heap. So in our max heap, it is not guaranteed that when we do a poll call, this node will be evicted first. It could happen that either of these two nodes can be evicted if we are only adding nodes to our max heap based on the node values. So if we want to evict the node which is closer to the top of the stack, then we want to keep track of the timestamp at which a particular node is added to our max heap. So in Java, a max heap is implemented as a priority queue. So we are going to have a priority queue of nodes, and in this node class, we are going to have value, and another field that we're going to have is a timestamp. So as we are creating new nodes through our push function, we are simply going to increment timestamp, and we can use a global variable like we used in our design Twitter question. And this way, when we do a push call, so the most recent node is going to have a bigger timestamp. In our priority queue comparator, we can check if the node values are equal, then we can check the timestamps and take the node which has a bigger timestamp. And this way, when we do a poll call, then the node with a bigger timestamp, it is going to be evicted first in case of duplicates. Now another challenge that we have to solve is this pop call. Now let's say a pop call comes in, and as we know, this node 3 is going to be removed from our doubly linked list, and this node 3 is going to be present somewhere in our max heap. So this is like removing a random node from our max heap, and if we implement this, then it is going to take O of n time to remove a random node from our max heap, and then our implementation of using max heap with doubly linked list is not going to satisfy the time constraints for this problem. So what we can do, that instead of removing it from the heap instantly in O of n time, what we can do is, as we are removing this node from our doubly linked list, we are going to mark it as removed. So to mark it as removed, we are going to use another boolean. Let's call it is removed. So this is going to be a boolean, and we are going to set this boolean for this node 3 as true. So once we do that, we are going to delay the removal of this node from our max heap, and this process is called lazy deletion. So this lazy deletion is used in some real world problems. If we are using lazy deletions, then we need to be careful about some things in our popMax functions and peekMax functions. So for, let's say, now when we are implementing our peekMax function, then it is not guaranteed that the node at the top of the heap, it is the real maximum value, because when we removed this node 3 from our DLL, we did not remove it from our max heap. Then we are going to check if this node has been marked as removed or not. If this has been marked as removed, then we are going to remove this node, and we are going to keep removing the nodes till we find a node which has not been removed. Then when we reach a node which has not been removed, then that is going to be our real maximum node. And similarly for our popMax call, we are going to do same thing, and once we reach the maximum node, we are going to get the reference of that node and we can remove it from our doubly linked list, and we will be done. Now using this approach, our top function call, it is going to be O of one time, because for our top call we are simply returning head.value, and that's it. We are not changing anything in the DLL or our max heap. For our pop call, we are removing the head node and marking that node as removed. So this is also going to take O of one time. For our push call, so adding it to our doubly linked list, that's simply constant time, and adding it to our max heap, it's going to be logarithmic time. So overall it is going to take O of log n time. Our peekMax function, on average it is going to take O of log n time, and similarly our popMax function, on average it is going to take O of log n time. For worst case scenario, these peekMax and popMax functions can degrade to O of n log n time when the real maximum node which has not been removed, it is deep down in our max heap. So in our second approach, we don't make use of max heap. Instead, we make use of a TreeMap. And in that approach, both the data structures are going to be in sync with each other. Now let's have a look at that approach. As compared to a hash map, a TreeMap keys are sorted in ascending order, and a TreeMap is implemented as a balanced binary search tree. In a hash map, the keys are not ordered, and to find the max key, we are going to have to iterate over all the keys, and it is going to take O of n time. For a tree map, however, we can find the max key in O of log n time. So this tree map is having the mapping from integer to a DQ. So this key 1, it's going to map to one node which has value 1. Key 2 is going to map to one node with value 2. Key 3 is going to map to one node. Key 4 is going to map to two nodes with value 4. And when we are adding the nodes to a DQ, we are adding it to the front of the DQ, so that we don't need timestamp and we can get the most recent node from the front of the DQ. So for our node, we only need the node value and we don't need timestamp, and also we don't need is removed boolean. Now when we do a push operation on the stack, we add it to the doubly linked list and we also add it to our tree map. So the push function is going to take O of one time for DLL and O of log n time for tree map. Top function is going to take constant time. Pop function is going to take O of one time for DLL and O of log n time to remove from tree map. And similarly, peekMax and popMax functions are going to take log of n time. Now let's write code for our first approach involving doubly linked list and a max heap. So here we have to implement these 5 functions, and we can assume that there is going to be at least one element present in the stack when we are making any of these calls. So to get things started, we can create our node class and define the fields in there. So first one is value, second one is going to be timestamp, third one is going to be a boolean is removed, and we are going to have a next reference and a previous reference, and we can create a constructor and pass in value and timestamp, and then we can assign these values. This dot timestamp is equal to timestamp, and inside our max tag class, what we can do is we can create the head of the doubly linked list and a tail of a doubly linked list, and we have to define a priority queue of nodes, and let's call it max heap, and we have to import this. I think it's already imported, so that's good. And inside our, and before going inside the constructor, we have to define a global variable timestamp and assign it to 0. And now inside our constructor we can create the head node, and let's say by default we give it -1, and similarly for tail we give it -1 for value and timestamp. And now we can set head dot next equal to tail, and tail dot previous equal to head, and we can initialize our max heap. Here it's going to be new priority queue of nodes, and inside this we have to pass in a comparator, new comparator of nodes, and inside our comparator we have to define compare function, public int compare, then node 1, node 2, and then we can take the difference of the values first, node 2 minus node 2 dot value minus node 1 dot value. So because we have to take the bigger value, that's why node 2 is on the left and node 1 is on the right. And in case the values are equal, so in that case diff is going to be 0, then we have to make timestamp the priority. So in that case we can do node 2 dot timestamp minus node 1 dot timestamp, and at the end we can return diff. And here what does it say? We have to also import comparator, so we can do import java.util.comparator, and yeah, now the error goes away. So we're going to need a semicolon here, and what does it say? Okay, yeah, so it can also be written as a lambda expression. Okay, so let's first think about our top function. So for our top function we are going to simply return head dot value, and we'll be done. And let's write our push function first. So for our push function, a new node is going to be added to the head of the linked list. So let's write new node x, and we have to save the next pointer, head dot next, and now we have to add this node between head and next. So what is going to be, head dot next is going to be equal to node dot next is equal to next dot previous is going to be equal to the node, and node dot previous is going to be equal to head. And once we do this, so why does it say error? Oh, we have to pass in the timestamp as well, timestamp plus plus, and now we have to add it to our max heap as well. So we can simply do max heap dot add, and we simply added our node. And now next, oh yeah, so for top it should be head dot next dot value, because head is a dummy node, head and tail are oops. So here head and tail are two dummy nodes. So the first node is going to be head dot next. So we have to update it to head dot next dot value. So for our pop function, what we can do is we can first define the node to remove. So let's call it node to remove, and this is going to be head dot next, and we can set head dot next equal to node to remove dot next, and node to remove dot next dot previous is going to be equal to head, and now we can mark it removed. So node to remove dot is removed is going to be equal to true, and at the end we can simply return node to remove dot value. So far we have implemented our three functions. So now let's think about peekMax and popMax functions. So for our peekMax function, at the end we know that we're going to find the maximum element at the top of the heap. So let's first write max heap dot peak dot value, And if we just do this, then it's going to give us wrong answer, because in our pop function we have delayed the deletion from the heap. So the heap might have some stale entries, so we have to return those stale entries. So what we're going to do is we're going to do a while check, while max heap is not empty and max heap dot peek dot is removed. Then what we are going to do, we are going to poll from our heap, max heap dot poll. And now we are going to get rid of all the stale entries, and at the end we are going to be left with the correct maximum value, and we simply return it. So, and for our popMax function, first again we have to remove all the stale entries. So what we can do is we can call peekMax function here, and now the node is going to be the maximum value, so we can call it max node. It's going to be max heap dot poll, and at the end we have to return its value. It's going to be max node dot value. So here we have removed it from our max heap, and we have to also remove it from doubly linked list. So to remove it from doubly linked list, we have already gotten the reference from the max heap. So what we are going to do is we are going to update the pointers, and to update the pointers, what we're going to do is we're going to set max node dot previous dot next equal to max node dot next, and we have to set the previous pointer of max node dot next dot previous. It is going to be equal to max node dot previous. So this way we have set the max node dot previous dot next and max node dot next dot previous, and this way we don't have any reference to max node anymore, and we have removed it from our DLL, and at the end we removed max node dot value. So this was the code implementation of our DLL and max heap using lazy deletion. I hope it made sense, and now let's move on to our next approach. Let's try and update this code to write the code for our second implementation involving doubly linked list and a tree map. So for the tree map implementation, we are only going to need the value, and we are not going to need timestamp and is removed. So let's remove that, and we are going to need the next and previous and the constructor. We can remove this dot timestamp, and we can remove the argument here, and we don't need this priority queue, and we don't need the timestamp. Similarly, we don't need this max heap here, and here we have to just pass one value and one value, and here I can create our tree map of integers and a DQ. It's going to be DQ of node, and I have to import this, so let's add import. So if I go all the way up, I can remove these two imports. So I have imported DQ and our tree map, and here I have to assign it some name. So let's call it map, and inside of our constructor we have to initialize this map. So what we can do is we can set new tree map integer and DQ of nodes. Now coming to our top call, so top call is going to remain unchanged, and let's think about our push function now. So in our push function, it's going to remain the same since we have our doubly linked list. So we are adding here to our doubly linked list, and here we can remove the setting of timestamp, and here instead of max heap we have to add it to our tree map. So what we can do is we can check if map dot contains key. If this map does not contain the key, then we have to put it in our map. So we can put map.put x comma, it's going to be new array dq, and it's going to be dq of nodes. And once we create the mapping for x, we have to get the key, and now we have to add it to our dq. So we can either add it to the end or we can add it at the front. So let's add it to the end of the dq, and at last it's going to be node. So this is our push function. For our pop function, what's going to happen is these three lines are going to remain unchanged, and we don't need this one. And now we have to remove from DQ. It's going to be node to remove dot value dot remove last. So since we were adding to the last of DQ, when we are removing it, we have to remove it from the last as well. Next, we have to check if the items in the DQ they become empty, then we are going to have to remove the mapping from our TreeMap. So we can do node to remove dot value is empty. So if it becomes empty, then we have to remove that key from our map. It's going to be node to remove dot value, and at the end we return node to remove dot value. And what's the warning? This is giving us assignment to itself. Okay, what's happening here? Node. No, it's fine. Okay, so next for our peekMax function. So since we know that the keys in a tree map are sorted, so it's going to be just one line. So we can simply return map dot last key, and this is going to give us the biggest key. And for our popMax function, what we can do is we're going to have to call the last key to get the key. It's going to be map dot last key, and then we have to remove it from our DQ. So previously we were getting it from our max heap, so now we are getting it from our DQ. So it's going to be map dot get key remove last. So when we get the reference, then we have to first check that the number of nodes in the DQ, if they become 0 or not. If they become 0, then remove that mapping from our tree map. So it's going to be map.get key is empty. Then we can simply do map.remove key, and now we can simply remove that node from our Doubly linked list. And at the end, what we can do is either we can return max node.value or we can return key. So yeah, let's have a look. Oh, what's the error here? Oh, we missed this one. Okay, so this was the code implementation of our TreeMap approach. If you have any doubts, let me know in the comments. I hope it made sense, and I'll see you in the next video.